Hi everyone, welcome to the class. Do let me know in the chat box if I am clearly visible and audible. And let me just inform the students that we are live. Okay, so let's start with group number 14. We have till now discussed about group number 13. Now we will be doing group number 14. Right, everybody? Ready? Shall we do group number 14? Right? So, what we have done till now, we have done. Okay. Till now, we have discussed till here. Right? Just give me a second. Okay. So, now we are going to start with group number 14 and we'll try to complete group number 15 and 16 as well as today. So, let's see if we can do that or not. Right, everyone? So, very good evening, Nala, Medico, Harshit. Yes. I think in 3 hours, 15, 16, 14, 15, 16. Sorry, my bad. 14, 15, 16, we can easily cover. Right? Let's see if we can do that or not. Right? So, 3 hour class or maybe 4 hour class it is going to be. So, let's see. Right? Okay? Okay. So now first thing that we have here is group number 14 elements, the carbon family. You have group number 14 elements, that is the carbon family. From the carbon family, what you have here, carbon, silicon, germanium, tin, lead. That is का सी गए संत प्रभु. Okay, Kasi gaye Sant Prabhu. That's how you can remember carbon, silicon, germanium, tin, and lead. Let me see if that is also visible. Right now, when you see this thing here, right, these are the elements, and now let's discuss what about these elements. What we are going to talk about these elements here: carbon, silk, germanium, tin, and lead, and flavorium. That is, we are not going to discuss this particular because it's a radioactive element. These are the elements of group number 14. Now, carbon is 17th most abundant element by mass in the earth crust. It is highly abundant. We are also made up of carbon, isn't it? It is widely distributed in nature as well as free in the combined state, like carbon monoxide. Free state, you have carbon coke, right? Then in the combined state, you have carbon monoxide, carbon dioxide, all these things you have here, right? Then in elemental state, it is available as coal, graphite, diamond. All these are the elemental state where carbon is connected to carbon only, right? Then, however, in the combined state, it is present in metal carbonates, hydrocarbons, in organic chemistry, carbon dioxide. You use all these things are present. One can empathetically say that carbon is most versatile in the world, right? We are made up of carbon, graphite is made up of carbon. Graphite is so cheap, right? It's used in lead pencils, right? Pencils it is used, so it's quite cheap, right? And diamond, it's so expensive. So can you see the difference, the versatility, right? So it can, according to its shape, it can be also in organic compounds. We also eat carbons from the organic compounds. We are also made up of carbons, and there is also coal that we cannot eat. There is also carbon monoxide that is very poisonous for us, right? So that's the versatility of carbon. Its combination with other elements such as dihydrogen, dioxygen, chlorine, sulfur provides astonishing array of material ranging from living tissues to drugs and plastics, right? Organic chemistry is all about carbon containing compounds. It is essential constant for living organism. Naturally occurring carbon contains two stable isotopes. Now we have two stable isotope of carbon, carbon 12 and carbon 13. In addition to these, third isotope is carbon 14 is also present, but that is radioactive. So which isotope is radioactive? Carbon 14 is radioactive in nature, right? Then its half life is 5770 years. Used for radiocarbon dating. Silicon is second most abundant element on the earth crust. It is so abundant. It is second most abundant earth crust and is present in nature in the form of silica, silicates, right? In ores it is present. Silicon is very important component. Ceramics, glass and cement. It is very important components of these ceramics, glass and cements. Right, this is about silicon. Silicon is second most abundant, carbon is 13 most abundant. Silicon is used, it is there in silica and all these things. You will see it there. Wait a minute. Yes. Okay. Then germanium exists only in traces. Germanium will only exist in the traces, ma'am. What kind of traces, ma'am, germanium exists? Like very rarely it exists, right? And what about tin? Tin occurs mainly in cassiterite and lead as galena. Now, these ores are important for you to remember. That I'll just highlight this as well. So, if you see this tin will mainly occur as cassiterite, that is SnO2, right? And lead as galena, that is PbS. These are the two ores that we have. Then, if you talk about flavorium, fla- flerovium is a synthetically prepared by radioactive element that we are not going to discuss at all, right? Ultra pure form of germanium and silicon are used to make transistors in semiconductors. So in physics you must have learned about semiconductors, right? So in semiconductors, N type, P type semiconductors, you used silicon and germanium, right, to make N type, P type semiconductor. That is ultra pure form of this that you have, right? Tell me, right, everybody? Okay? Yes. Yes, everybody, tell me. Yes? Got it? Whew. Now let's see the next thing. Symbol of flavorium is Fl. It has atomic number this, atomic mass this, da, 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 da. You don't need to do that. It has been produced in only small amount. Its half life is short. Its chemistry has not been established yet. Right? It's a radioactive element, so we have not studied it. The important atomic physical properties along with their electronic configurations of the elements leaving fluoronium all are discussed here, right? Let's see. So we'll understand it from the electronic configuration. First thing is, what is the electronic configuration? Ma'am, electronic configuration is Ns to Np2, right? So how many electrons it has in the outermost shell? It has 4 electrons here, right? It has 4 electrons, guys. Now, when I say it has 4 electrons, in that one thing should be clear in your head, that here higher oxidation state is nothing but that is +4. Lower oxidation state is +2 here. That is of only p orbitals, right? Now, one by one, we'll discuss about this. Full chart should be on your tips, right? This is the chart that we're going to discuss now. Let's discuss about this chart, right, everyone? Shall we discuss this chart? Tell me, everybody. Shall we discuss this chart, right? So one by one, we are going to discuss it. Let's see how. Okay, let's see how we are going to discuss this. So, if you see, first thing is physical properties, and one by one, I'm going to discuss it. First thing is physical properties. There, what we have, all members of group 14 are solids. All the members are solids here. So that is a very important fact. All members of group 14s are solid, right? Carbon, silicon. If you talk about carbon and silicon are non-metals. Germanium is a metalloid. Tin and lead are soft metal, and this is a very important point here, that silicon is a carbon and silicon are non-metals. Germanium is a metalloid, very important, whereas tin and lead are soft metals. Okay, that you must know about every which one is metal, which one is non-metal, right? Then one thing with low melting points, that means tin and lead are going to have really low melting points. Melting and boiling points of group 14 elements are much higher than those of corresponding group 13. So you can write this over here, that melting point of group 14 is much higher than melting point of group 13. Okay, as compared to the elements that we have discussed before, they will have more melting point. Now I'm going to tell you about, if you see the melting point over here, what you will see, it has higher melting point. As you can see, melting point is higher, but can you see this is of the range 1200, it is suddenly lead and tin are really less. So that means lead and tin has very low melting point as compared to their state here, right? Okay, so you can say this over here, that melting point, or you can just write this thing here, lead and tin, they will have low melting points as well. So you can write this here, that lead and tin have low melting point. Okay, now let's talk about other properties here. Electronic configuration we have discussed. Let's discuss about the covalent radius. What will happen to the covalent radius? Right, everybody? If you see covalent radius, there is considerable increase in covalent radius from carbon to silicon. From carbon to silicon, there is considerable increase, right? And then after silicon to lead, a small increase in radius is observed, right? That means it is increasing only, but from carbon to silicon, I'll just show you the chart here. If you see, atomic number is there, atomic mass, electronic configuration, covalent radius, you will see 77 to 118. Carbon to silicon, there is a big large gap is there, right? Then suddenly little bit 4, then it is increasing by units of 10, right? Then it is increasing by units of 6. So that means very small increases there. So what you can write for the covalent radius here, you can write carbon, then it is increasing, right? Ka si gaye sant prabhu. It is increasing only, but in case of carbon silicon, there is a big increase, right? Others will have small increase in the radius. Okay, this is what we are going to write here. Understood? Yes, everybody? Tell me. Firstly, let me complete P block, then we'll start that as well. But if the students remains like this only, then I'm not going to cover, right? So I'll see like how many students are there in the class, right? If you guys are interested, then definitely we'll come up with something. But if you guys are not interested, then guys, then whom we are teaching, right? Now let's talk about ionization enthalpy. First ionization enthalpy of group 14 element is higher than that of corresponding group 13 element. So in group 13, what you have? You have NS2NP1. Here you have NS2NP2, where it will be easier to take out electron. Obviously, here it will be easier to take out electron. Here it is easy to take out electron. Here it is difficult to take out electron. Can you tell me why? Here it is easy to take out the electron because it will be getting converted to ns2. Here it is getting converted to a stable configuration. This is getting converted to ns to np1, which is not a stable configuration. Then you can't say that this is going to be 0. Okay, got it? So that's why we can say that first ionization enthalpy, you can write it over here, that first ionization enthalpy of group 13 is going to be less than first ionization enthalpy of group 14. Here if it is easy, that means less energy is you can say less energy is required. Here more, in this case more energy is required. In this case less energy will be required, right? Because of that particular reason. Now next is the first ionization enthalpy of group 14 members is higher than the corresponding members of group 30, that we have discussed. The influence of inner core is visible here also. Inner core influence will always be visible because of addition of d electrons, because of addition of f electrons, right? In general, the ionization enthalpy decreases down the group. What we'll see, size is increasing, ionization enthalpy is going to decrease down the group, right? Decreases down the group, small decrease from silicon to germanium to tin, slight increase from tin to lead, right? So what we have, small decrease is there, then there is increase, right? So is a consequence of poor shielding effect of intervening d. See, reason is always going to be poor shielding effect of d and f orbitals, but that's why what is important for you to understand the this, wait a minute, let me just show you that what is the trend here. Ionization enthalpy, can you see that it is decreasing, it is decreasing, it is decreasing, then it is slightly increasing. So all of that, firstly there is large decrease, then there is small decrease, then there is small increase. This is what we can see over here, right? So I'll just write it there, I'll just zoom it in. So what we are writing, we are saying ionization enthalpy, ionization enthalpy decreases down the group, small increase, firstly so there is large increase, small increase from silicon to germanium to tin, slight increase from tin to lead, right? So what you can see, I'll just write this over here. Mm, okay, firstly there is small, very large decrease, then there is large decrease means this thing, very large decrease, then small decrease, then there is slight increase. Okay, that is the order of ionization enthalpy, right everybody? Okay, I'm giving you all the orders by matching it with the your data that is given in your NCERT, because in the end whatsoever is written in any other book, what is important for you to remember the data of your NCERT. According to your NCERT you will remember that. Next is electronegativity. Due to small size, the elements of this group are slightly more electronegative than group 13 elements. Along the period, electronegativity increases. The electronegativity, now this is a very important question that they have already asked. In JEE, they have already asked this. The electronegativity values for elements of silicon to lead are almost the same. See what you have seen from the data itself, what you will see from the data itself. This is electronegativity. It is decreasing, it is same, which is same silicon, germanium and tin. They are same. Then lead is slightly above that. So what you can see, electronegativity decreases and then it is same. So I can just write it here. काशी गए संत प्रभु. Now firstly what we have seen that in case of carbon, okay, when you have carbon, what you will have here, wait a minute, what you will have here, carbon is decreasing, electronegativity decreases, then it is same, then it is here, it is decreasing to large amount, but here it is increasing to very less amount. That is the order of electronegativity. Okay, that is the order of electronegativity, right? That's how you can write the electronegativity order. Or you can also write it like this, okay, or you can also write it in a different way, that is, you can also write it like this. Carbon, then lead, then you have silicon, germanium and tin. First it is decreasing, then these are equal, then again it is less, slightly less, it is highly, because this is 2.5, this is 2.5, this is 1.9, then they are becoming equal here, silicon, germanium and lead are equal, so we'll just equate them. Okay, this also you can write down that this is also, we can write that this is the order. Okay, right everyone, tell me, clear? Clear? Okay, I would advise you to write this way only. Right, I would actually advise you to write ionization and enthalpy also this way only. Where should we write it? If we write ionization and enthalpy, carbon firstly, then you have silicon, then you have germanium, then you have lead and tin. Okay, so I'll write the ionization enthalpy order also like that. Okay, so it will be carbon, silicon, काशी गए संत प्रभु. Now it is decreasing only, so we are writing it in the decreasing order. So you can see that abnormality is in the end. In the end you can see that there is one abnormality here, right? There is one abnormality in the end here, right? Okay, tell me. Clear, students? So now from this table, what we have discussed, atomic number, mass, equivalent radius, ionization and electronegativity. Density follow a simple pattern here. It is increasing only, right? And what about melting point and boiling point? Let's discuss about melting point and boiling point. Melting point, we can see this over here, that melting point is decreasing, decreasing, decreasing. Then for lead and tin, it's very less. Lead and tin has minimum melting point. What about boiling point? Boiling point, is not boiled, and rest of them are decreasing, decreasing, decreasing. So you can see, you can just write it down here that melting point and boiling point both are going to increase, right? Melting point and boiling point both will increase, but melting not increase, they are going to decrease. Okay, both will decrease, while melting point of lead and tin is very low, exceptionally low, is quite low among this. Okay, it is exceptionally low. Okay, right? Tell me. Okay. Yes, everybody. Do let me know if that is clear. Tell me. Is that clear? Hmm. Why the students has not joined today? That's what I'm thinking. Why the students have not joined today? Hmm. You want me to disappear again? Huh? Why you have not joined it? I think maybe on the last point I have told you, maybe that's why. Chalo, koi na. Let's see. Next thing, let's see. Chemical properties. Let's talk about chemical properties, guys, now. Let's see. First thing is oxidation states and trends in chemical reactivity, right? So now let's talk about group 14 elements, that is have 4 electrons in outermost shell. Group 14 elements, they have 4 electrons in the outermost shell. We know that the common oxidation states is exhibited by is plus 4 and plus 2. Plus 4 will be higher oxidation state, plus 2 will be lower oxidation state. Carbon also exhibit negative oxidation state since the sum of first 4 ionization enthalpy is very high. First 4 ionization enthalpy is very high. So carbon, instead of losing 4 electron, it would want to gain 4 electron. Because its first 4 ionization is very high, it is not able to lose 4 electrons. It will gain those 4 electrons, right? Since the sum of first 4 ionization enthalpy is very high, compounds with plus are generally covalent in nature. Very important. Ma'am, what is there? Right? Uh, First 4 enthalpies of carbon is very high. That's why compounds in plus 4. That's why first thing is carbon also exhibits negative oxidation states. Negative oxidation states it will exhibit like minus 4 or sharing of electrons, right? Now we are saying its first 4 ionization level is very high. That's why in plus 4 oxidation state generally covalent in nature. That means carbon, in a simple way, you know what you can write here? Carbon is not able to, you can write here in a simple way, carbon is not able to lose electrons, so it will share electron and form covalent bond. Okay, I think that much you can write. So it will share the electron because it cannot lose the electron, so it is going to share the electrons, right? In heavier members, the tendency to show plus 2 oxidation state increases because lower oxidation state increases down the group. It is due to inability of, again, it is inert pair effect. D orbitals, F orbitals does not have a good screening effect. The relative stability of these two oxidation state vary down the group. Carbon and silicon mostly show plus 4. Germanium forms stable compounds of plus 4 state. Only few compounds in plus 2 state, that tin forms compounds in both, only few compounds are stable in plus 2 state. Kasi guys, Sant Prabhu, that means tin and lead are forming plus 2 state. Tin forms compound in both oxidation state. Tin in plus 2 state is reducing agent. Why tin in plus 2 state is reducing agent? You know what we have seen. What is there? Kasi gaye Sant Prabhu. Actually, tin is stable in plus 4 state, lead is stable in plus 2 state. Because most of the compounds wants to be in plus 4 state, but tin, because down the group the stability of plus 2 oxidation state increases. That's why this is a very famous question of your NEET exam, that Tin, wait a minute. Tin in plus 2 oxidation state is acting as a reducing agent. It's a very famous question. Let's see how. If you see tin is in plus 2 state, okay? Tin is in plus 2 state. Tin is in plus 2 state as it is more stable in plus 4 state. So its oxidation number will increase. It will itself be oxidized. That's why it is a very good reducing agent. That's why it's a good reducing agent. But but lead in plus 2 state are stable. We know that lead in plus 2 state are stable, and in plus 4 state are strong oxidizing agent. So we can say that lead in plus 4 are strong oxidizing agent. Can you tell me why? Again, the reason is same. Reason is same, guys, here. Right? So this is lead in plus 4 oxidation state. This is lead, guys. Okay. Now, if I say this here, lead in this is plus 4 oxidation state. This will go to plus 2 oxidation state because here plus 4 oxidation state is more stable. Here plus 4 oxidation state is more stable. Here plus 2 oxidation state is more stable. Okay. That is the reason lead is getting converted to plus 2. That means oxidation number is decreasing. That means it itself is getting reduced. If itself it is getting reduced, that means it's a very good oxidizing agent. Right? It will act as a very good oxidizing agent. Then in tetravalent state, the number of electrons around the sentimental atom, for example, carbon in CCl4 is 8. Its octet is completed. Being electrons precise molecules, they are normally not expected to act as electron donor or electron acceptor because they have 8 electrons. They don't need or they don't want to gain or lose electrons because it is not needed here, right? Although carbon cannot exceed its covalency more than 4. Now, ma'am, why it cannot exceed its covalency more than 4? Any one of you who knows the answer for this one? Do you know the answer for this one? Tell me. Do you know the answer for this one? I was texting you since a month, ma'am. Please respond. Where, Nala? Where have you Where have you texted? Uh, okay. Welcome, welcome, NEET aspirant. Yes. Okay, Chandra. Yes. Okay. See, now it is not extended. Its covalency is not getting extended. So we're just gonna write it here. Although carbon cannot exceed its covalency more than 4. Why? Because it is the first element. No first element can exceed its covalency. I'll see that, Nala. I have not seen it. Right? The schedule is quite tight. You know that today also I took 3 hours class in DNA. So that's why the time I'm not getting only. Right? So next is other elements of group can do so. It is because of the presence of d orbitals in them, because they have the presence of d orbitals. That's why they can expand their covalency. Due to this, their halides undergo hydrolysis and have tendency to make complexes by accepting the electron pair from the donor species. So that is the reason you will have tin also with expanded covalency, silicon also, germanium also, but you will not have carbon in this form. Carbon can only form tetrahedral, right? Okay, tell me. And that's why we can see that all of these have 6 bonds. That is why their hybridization is going to be sigma plus lone pair. That is 6. That is sp3d2, right? Okay. Now let's see the reactivity towards oxygen. All members All members when heated in oxygen form oxides. All members when they are heated in oxygen, they are forming there are mainly two types of oxides, monoxide and dioxide of formula MO. Monoxide is of this formula, dioxide is of this formula. These two oxides they will have, right? SiO, now this is important. SiO only exists at high temperature. Oxides in higher oxidation state of elements are generally more acidic than those in lower oxidation state. For example, now this is extremely important, that CO2, SiO2 and GeO2, right? Carbon, silicon and germanium, their oxides are acidic, whereas tin and lead, they have amphoteric oxides, right? Among monooxides, what you have, CO is neutral, germanium oxide is acidic, tin and lead oxides are amphoteric. So this is quite important. This is very important. This particular part that I have written here, this is important. Okay, you must know the acidic basic nature of these oxides. Okay, I'll surely see your chat. I'll surely see your chat. Wait a minute. I think I'm getting cut again and again. Okay, I'll surely see your chat. Don't worry about that. Right? Okay, tell me. Clear? Clear, everyone? Tell me about it. Whew. Okay, next let's see reactivity towards water. Let's see the reactivity towards water, right? Okay, let's see the reactivity towards water. Yes, everyone, let's talk about that. So, reactivity towards water, if you see, carbon, silicon, germanium are not affected by water at all. Tin decomposes steam to form, decomposes in steam to form dioxide and this dihydrogen. So, tin will react with steam. Lead is unaffected by water, probably because of protective oxide formation. So, tin is the only thing which is affected. Tin decomposes steam to form dioxide and dihydrogen gas. Other will not react. Others will not react. So, you can write only tin reacts. You can write here only tin will react here, others will not react here. Acha, now let's see reactivity towards halogen. These elements can form halides of the formula mx2 and mx4. Wait a minute. So if you see this here, these elements can form halides of the formula mx2 and mx4. Now why ma'am mx2 and mx4? So simple thing is, M is what? 4 positive or it can be 2 positive. So X is negative negative. Here cross multiplication they will form mx4, here they will form mx2. Right? Now let's discuss this. What we are saying, except carbon, all other members react directly with halogen under suitable condition to make halides. Carbon will not do so, right? Most MX4 are covalent in nature. Central metal atom of these halides undergo sp3 hybridization because of 4 sigma bonds. The molecule is tetrahedral in shape. That also we know sp3 means it is going to be tetrahedral. Exceptions, now this is main point which we are going to focus here. What are the exceptions here? Exceptions are that SnF4 and PbF4, which are ionic in nature. This is very important point, that SnF4 and PbF4 are ionic in nature. Others are not ionic, but these are ionic in nature. Okay, these are ionic in nature, right? So what we have told here, that these are ionic in nature. Exceptions, these are among the exceptions. Then we have, let's discuss, PbI4 does not exist only because, reason also very important, because assertion reasoning question can be asked here. See, we are saying that all the halides are covalent in nature except for these things, except for SN F4 and PbF4, they are ionic in nature. Then we are saying that PbI4 does not exist only. Does not exist. Why? Because PbI bond initially formed during the reaction does not release enough energy to unpaired 6s2 electrons and excite one, and excite, this is reason is also very important, excite one of them to higher orbital to have four unpaired electrons around the lead atom. So I'll now just explain that what we have said here. See, this whole line is quite important. We are saying that PbI4, this will not exist, that is the assertion. But why it is not existing? So this can be your assertion reasoning question. Assertion reasoning question. Okay. Why it is not existing? Because PbI bond initially formed. If I say PbI bond that is getting formed, the reaction does not release enough energy to unpair 6s2 electrons and excite one electron. That means when this bond is getting formed, it is not releasing enough energy to unpair 6s2 electrons and excite one of them to higher orbital to have four unpaired electron around the lead atom. Because what should happen when one bond is getting formed, it should release some amount of energy so that other four bonds can also get formed. But this first bond is only not releasing enough energy for the other bonds to get formed, right? So in 6s2 this will not get unpaired. So for bond formation you need to have half filled orbitals, that will not be there. So that is the reason PbI4 does not exist. That's a very important question. Okay, next is heavier members of G to the are able to make halide formula. This heavier members will, because they are more stable in +2 oxidation state. Stability of dihalides increases down the group. Down the group, the dihalides, their stability will increase. Considering the thermal and chemical stability. Ma'am, what do you mean by thermal and chemical stability? Considering the thermal and chemical stability, GeX4 is more stable than GeX2. Why? Can you tell me? According to the thermal and chemical stability, GeX2, right? GeX4 is more stable than GeX2 because germanium is more stable in +4 oxidation state, whereas lead is more stable in +2 oxidation state. So PbX2 is more stable than PbX4. Another important point. So these are all the points which they can ask you directly. I'm highlighting all the important lines here. Now we are saying that except CCl4, other tetrachlorides are easily hydrolyzed. CCl4 is not easily. CCl4 is not easily hydrolyzed. So you must write it here. CCl4 not easily hydrolyzed. Can you tell me? Because carbon cannot expand its covalency, right? By water, because central metal atom can accommodate lone pairs of electrons from oxygen in the d orbitals, because other can accept, right? You can just write it here. except carbon, except carbon, others can expand their covalency. That is the reason behind this. Except why? Why CCl4 other electrolytes are easily hydrolyzed? Reason is this. Okay? In fact, instead of doing this here, I'll just put this here. Okay? Covalency. Right? Okay? So why CCl4 except CCl4 other are easily hydrolyzed? Because except C, all other can expand their octet. So in an easy language, I am writing it, right? So this also we have done. Then hydrolysis can be understood by taking example of SiCl4. It undergoes hydrolysis by initially accepting lone pair of electrons from water in the d orbitals, finally leading to the formation of SiO4 below. So what exactly it happens? It will accept the lone pairs, right, in the d orbitals, then Cl negative will leave, and that's how you will have the formation of SiOH4, right? Okay. Or you can, instead of expand their covalency, you can write except carbon, others can. What they can do? Except carbon, others can accept lone pair in d orbitals. In their d orbitals, they can accept the lone pairs. Okay, got it, everyone? Tell me. Done? Shall we move ahead? Let's see this. Okay. Important trends and anomalous behaviors that we are going to discuss now. Let's discuss that. Important trends and anomalous behavior. So, what we have here, let's see. In important trends, what we have, important trends and anomalous behavior of carbon, it is the same thing that we have discussed, just some important different things will be there. Like first member of other groups, carbon also differs in rest of the members. Why? It is again because of smaller size, higher electronegativity, higher ionization enthalpy. Instead of this now, I'll not highlight this with a highlighter. It's not that important. Everything is getting repeated here. Why carbon shows anomalous behavior? Because of these things. Then carbon only S and P orbitals are available for bonding. Therefore, it can accommodate only 4 pair of electrons. This would limit the maximum covalency. Whereas in other, they can expand their octet. Right? So the crux of this thing is others except carbon can others except carbon can expand their octet. Okay, they can expand their covalency. Then now carbon also has this unique ability, to form p pi p pi. That's why C double bond O, C double bond C, C triple bond, all these things you will see with itself and with other smaller size, other atoms of small size and high electronegativity. Heavier elements do not form p pi bonds because of their atomic orbitals are too large to diffuse to have effective overlapping. 2p 2p, see, this is having 2p, this is also 2p. This is 2p, this will have also 2p. This will be 2p, this will be 3p. This will be 2p, this will be 2p. So they can have effective overlapping. but higher orbitals cannot have effective overlapping. So you can say that they form ability to form p pi bonds, they can form, right? But higher members cannot. Heavier members do not form p pi bonds. Okay? Right? Because of overlapping is not. Because this also they can ask you in the question form that heavier members, heavier elements, right, do not form p pi bonds. What is the reason? What is the reason? Tell me. Ma'am, the reason is because their atomic orbitals are too large to diffuse to have a effective overlapping. Okay, they can ask you assertion and reasoning. Reasoning, what is written in the NCERT, that reasoning is the applicable reasoning, okay? Or in and around that reasoning. Next, guys, we have carbon atoms have tendency to link with one another through covalent bonds. They can form covalent bonds to form chains and rings. That property is called as catenation. That is the self-linking property of carbon. Self-linking property of carbon. This is because CC bonds are very strong. Down the group, the size increases, this decreases, there have a tendency to show catenation decreases. This can clearly be seen from the bond enthalpies value. The order of catenation decreases down the group. Lead does not show any. Now they can ask you, which of the following members do not show any catenation? So we can say catenation decreases, but lead will not show any kind of catenation, right? So you can say the order of catenation is this. This is the order of catenation. The order of catenation is decreasing and lead will not show any kind of catenation. Okay? Can you see this over here? How we are highlighting the important points, right? Okay? Tell me. Understood? Understood, everybody? Understood, everybody? Right? So, next is that we have discussed. Now, what about the next thing? What about the next thing? This is bond enthalpy, right? Now, what we have? Bond and bond enthalpies here. Let's discuss that. Bond enthalpy. Carbon carbon very high, then it decreases, decreases, decreases. So down the group BDE, bond association enthalpy decreases because the size increases, electron negativity decreases. That is the reason, right? Due to the property of catenation in p pi, carbon is able to show allotropic forms in which it exists in different allotropes, right? So carbon exhibit many allotropic forms, both crystalline as well as amorphous. Diamond and graphites are too well known. Now, students usually don't know which is crystalline, which is amorphous. Diamond and graphite, these are crystalline allotropes, okay? And fullerenes, they are amorphous, right? Discovered by this, for this discovery they were awarded the Nobel Prize. This is amorphous allotrope. Then we have diamond. What we are going to discuss in diamond, it is a crystalline lattice. It is a crystalline lattice. That's why it crystallizes, it gives you glow, right? In diamond, each carbon undergoes sp3 hybridization because each carbon is connected with 4 carbons, right? So each carbon, you can say, is under sp3 hybridization, linked to 4 other atoms by using hybridized orbitals. The CC bond length is 154. The structure extended chain produces a rigid 3-dimensional network of carbon. This is the kind of structure that is there. Each carbon, 1, 2, 3. Wait a minute. It should be one more bond here. So each carbon is bonded to 4. This carbon 1, 2, 3, 4. This carbon 1, 2 and 3 and 4 will be there. 1, 2, 3, 4. Then this is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So each carbon is connected to 4 more. Ma'am, here why not 4? Array 2, it is, they are just not showing it. Otherwise, it's a big structure. Right? Then next is they have covalent bonds. There is covalent bonds, right? It is very difficult. Now, why the structure? Why it is the hardest material known? It is very difficult to break extended covalent bonding, and therefore diamond is hardest substance on the earth, right? So what is difficult? It is difficult to break the extended covalent bonding, and diamond is the hardest substance on the earth, right? It is used as abrasive for sharpening hard tools, right? Then in making dyes, in the manufacture of tungsten, filaments for electrical bulbs, right? These are the uses of these diamonds. No doubt we use it now. Diamond is covalent, yet it has high melting point. Reason? Because of its three-dimensional network of strong CC bonds, which is very difficult to break, right? And that's why it has a very high melting point. Okay. Next is graphite. Let's do graphite now. Let's do graphite. Let's do and understand graphite. Right? Let's see. If you talk about graphite, graphite has layered structure. How the structure is? This is how the structure is. One layer, second layer, and this is the third layer, right? And if you see each layer, it has hexagon connected to another hexagon, connected to another hexagon, connected to another hexagon, connected to another hexagon. Okay, its hexagons are connected by covalent bonds, and each carbon is making just three bonds, just three bonds. That's why one electron is always free. One electron free for each carbon. That's why it is having very good electrical conductivity. And these are van der Waals forces. These are van der Waals forces. Right? How the rings are, hexagonal rings are connected as covalent bond, and how these sheets are connected as hexagon. So what you have here, layers are held by van der Waals forces between two layers. Each layer is composed of planar hexagonal rings of carbon atom. Right? Each carbon atom in this ring is sp2. Why? This is very important. Here each carbon is sp3. Here each carbon is sp2 because here you have four bonds. Here you have three bonds. That is the reason. Okay. Then each carbon is hexagonal rings of this makes three sigma bonds with three neighboring carbon atoms. 4 electron forms pi bond. Fourth electron, that means it is delocalized throughout. This is important. Fourth electron that is there, that is a free electron, forms pi bond. The electrons are delocalized over the whole sheet. That is why electrons are mobile, and that is why they are graphites. That's the reason graphite conducts electricity along the sheet. Along the sheet, it will conduct the electricity. Graphite, if you see, cleaves easily between layers, and therefore it is very soft and slippery. Ma'am, where we can see graphite, pick out a pencil, the lead of that pencil is graphite. Okay, so it's also very soft and it's also very slippery, right? Very soft and slippery because the van der Waals forces are not strong here. For a reason, for some reason, very soft and slippery. Then For this reason, graphite is used in dry lubricant in machine running at high temperature, where oil cannot be used as a lubricant. That's why, because it's soft and slippery, it's a good conductor. That's the reason it is used in machines under high temperature. Okay, right. Then the last one is fullerene. That is another allotrope. Fullerene are made by heating graphite in an electrical arc. So you have an electrical arc. Fullerene are made by heating graphite in an electrical arc. Right? It is like not natural, it's man-made. Right? So electrical arc in the presence. Now from where fullerenes are made? Fullerenes are made by, you can just remember, fullerenes are made by graphite. Just remember this thing. The sooty material forms by condensation or vaporization of CN small molecules, consist of mainly 6 C60 with smaller quantity of C70 and traces of fullerene with even number of carbon atoms up to 350. We are here discussing about C60. Fullerenes are only pure form of carbon because they have smooth structure without having dangling bonds. Fullerenes are cage-like molecule. They form like a football. They form like a cage, right? C60 molecule has shape like saucer ball, right? So C60 we are going to discuss that has a shape like saucer ball, and we can say this over here, and it is also called as Buckminster fullerene. Okay, it is also called as Buckminster fullerene, right? C60 has a shape like saucer ball, and that is also called as Buckminster fullerene. Okay, it contains, now this is highly important, it contains 20 it contains 26 membered rings. 26 membered rings are there and 12 5-membered rings are there. This is important. A 6-membered ring is fused with 5 or 6-membered ring, but a 5-membered ring can only fuse with 6-membered ring. That means we are saying that a 6-membered ring has only one option. A 6-membered ring is fused with either 6 or 5-membered ring. It can fuse with anything, but 5-membered ring can only fuse with 6-membered ring. You can also see this over here. A 5-membered ring, it is fused with 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 6. 6. And this is 6. And this is 6. Even if I draw it with different pen, what you will see, this is 6. Okay, this is 6-membered, this is 6-membered, this is 6-membered, this is 6-membered. A 6-membered ring here is fused like that. Okay, so a 5-membered ring, as you can see, is fused with 6-membered ring only. But a 6-membered ring, this ring can also have a 5-membered ring, or it can also has a 6-membered ring. Okay, right? Then here also they can ask you, all the carbon atoms are equal, they undergo sp2 hybridization here. So the hybridization is sp2 hybridization. Each carbon atoms form 3 sigma bonds with other carbon atoms. The remaining electron at each carbon is delocalized. So here also, just like graphite, this is also delocalized, right? Each carbon 3 sigma bonds it is forming. Remaining electron at each carbon is delocalized, just like graphite, within, and give aromatic structure, and this is aromatic in nature, aromatic character to the molecule because of that extra one electron, right? This is ball shaped molecule with 60 vertices and each one is occupied by one carbon. It also contains both single and double bonds because of that electron. with carbon carbon distance this and this respectively. Spherical fullerenes are also called as bulky balls. Okay, they are also called as bulky balls. Okay, right, all the important points guys I have highlighted here. Okay, now let's see. It is very important to know that graphite is thermodynamically most stable allotrope of carbon. Now, this also is a very important line. The most stable graphite is thermodynamically most stable allotrope of carbon, and therefore the formation of graphite is taken as zero. This you must have learned in thermodynamics, that the formation of graphite is taken as zero, the enthalpy is taken as zero, and the formation of delta H formation of diamond and fullerene, they are not zero, are this and this respectively, so they are not equals to zero. Only graphite is equals to zero because of its it is very thermodynamically most stable allotrope of carbon. Other forms of elemental carbon like carbon black and this are impure forms of graphite and fullerenes. Carbon black is obtained by burning hydrocarbons in limited supply of air. Charcoal and coke are obtained by heating wood, coal, respectively, at high temperature in the absence of air. So these are the other forms of carbon. Okay. Tell me. Hmm. Okay. So next is, if you see this here, next is uses of carbon. Now we have graphite fibers embedded in plastic material form high tensile. So these are the uses of carbons. Let's see that. Graphite fibers embedded in plastic material forms high strength, lightweight composites. The composites are used in products such as tennis rackets, fishing rods, aircraft, all these are uses. Now it's a good conductor, so graphite is used in electrodes as well. Crucible made from graphite are inert into dilute acids and alkalis. They don't react with that. Being highly porous, activated charcoal is used in absorbing poisonous gases. This also is very useful in our daily life as well. Not in our daily life, that means in so many ways it is used, right, in in our lives, right. Then air conditioning system to control odor. Carbon black is used in black pigment in black ink as a filler in automobile tires. These are all the uses. Diamond is precious stone used in jewelry and carrots and all, you know that, right? Okay, so this is where it is used. So let's see some important compounds of carbon and silicon now. Though from here some very selective things we are not going to do. We are not going to do full-fledged reactions here. Okay, till now I have taught you every single line, but now I'll be skipping few things here because these reactions and all only few are important for you, and that too because they are related to something else. Okay, right? Tell me. Hmm. Or shall I give you break of 10 minutes now? Okay, let's take a break of 10 minutes. Then I'll come back and then we'll see some important compounds of carbon and silicon here, right? That we have. As though that much we don't have here. Chalo, let's do it now only. Okay, because after the break, let's start with group number 15. Right? Okay. Right? Tell me. So, some important compounds of carbon and silicon. Oxides of carbon. Two important oxides of carbon are carbon monoxide and carbon dioxide. Carbon monoxide, how it is prepared: carbon plus oxygen, partial supply of oxygen. On small scale, pure CO is prepared by dehydration of formic acid. This also you can know that by dehydration of formic acid you have formation of carbon monoxide. Now what is important for you here? The mixture of CO and H2, that is called as water gas or synthesis gas, right? That is formed with when carbon and water they react at this much high temperature. Water gas is formed. When air is used instead of steam, a mixture of CO and N2 is produced. And you know what is a mixture of CO and N2 called? That is called as producer gas. Okay. Then water and producer gas are very important industrial fuels. Carbon monoxide and water and producer gas can undergo further combustion, forming carbon dioxide with liberation of heat. Is colorless. What kind of gas it is? It is colorless, odorless, and almost water insoluble. It is powerful reducing agents, that you must know that it is a very powerful reducing agent. It reduces almost all metal oxides other than those of alkali and alkaline earth metals. It's a good reducing agent, right? And so it is used here, like it is converting this Fe3 positive to 0. 3 positive to 0 means oxidation number here is decreasing. So it is reducing something. So there it is, carbon monoxide is behaving as a good reducing agent. CO molecules, now this is important for you. CO molecule, there are 1 sigma and 2 pi bonds between carbon and oxygen that looks like this. Okay, 1 sigma and 2 pi bonds are there. Because of presence of lone pair on carbon, CO molecule act as donor because it has a presence of lone pair and reacts with certain metal when heated to form metal carbonyls, right? So metal carbonyls that we have discussed in DNF log, they are formed here. Highly poisonous CO arises because it's, now we are saying highly poisonous nature of CO arises. Why it is so poisonous? Because why CO is poisonous? Tell me. Why highly poisonous nature of CO arises? Because of its ability to form a complex with hemoglobin. With our hemoglobin, it is able to, it has more affinity as compared to oxygen, right? Which is about 300 times more stable than oxygen hemoglobin complex. This prevents hemoglobin in the our blood cells from carrying oxygen around the body, ultimately resulting in death. That means instead of oxygen, our hemoglobin start carrying carbon monoxide because it has 300 times more affinity, and that is the reason that is poisonous for human body. Okay, next is carbon dioxide. Now, carbon dioxide in the laboratory, this is not important. It is colorless, odorless, low solubility, makes it immense good importance. Carbonic acid is formed. Acha. Once we know that it forms carbonic acid with water, which is a weak dibasic acid. Okay, it's a weak dibasic acid. As you can see, it dissociates, but it's a weak acid. Okay, what is happening here? Okay. ठीक है. Right? So now another important thing, that this you must have studied in ionic equilibrium as well, that what is the buffer inside our blood. Inside our blood, the buffer is H2CO3, and this buffer system helps to maintain pH of the blood between this and this. So in our blood, the buffer is carbonic acid and bicarbonate. That is the buffer that we have, right? So being acidic in nature, it combines with alkali to form metal carbonyls, right? And carbon dioxide is normally present in 0.03%. It is measured in atmosphere, and it is also removed from it by the process of photosynthesis, because in photosynthesis, plant, it consumes water and carbon dioxide to form oxygen and glucose, right? So it is a process by which green plants converts atmosphere, and this is a process of photosynthesis where CO2 is being converted to O2, that you can see here. By this process, plants can make their foods. Unlike CO, it is not poisonous. Carbon dioxide is not poisonous. It's not good, but it's not poisonous. But it increases the combustion of fossil fuels and uh, decomposition of limestone for cement manufacturing in recent years seem to be increase the CO2 content, that leads to now increase in CO2. When you have increase in CO2, that leads to greenhouse effect. Global warming is there. The temperature of the earth will rise. It's not poisonous, but it's also not good for the environment, right? It's a slow poison, you can say. Thus, raise the temperature of the atmosphere, right? Carbon dioxide can be obtained solid in the form of dry ice. There is also a solid form, solid carbon dioxide, that is called as dry ice. That is allowing this to expand rapidly. Dry ice is used as refrigerant for ice creams, frozen food. Gaseous CO2 is extremely used into now gaseous CO2 is used in soft drinks, right? Being heavy and non-supporter of combustion, it is used in fire extinguisher. This is also important. It is used in fire extinguisher, right? It is used as extinguisher, right, to decrease the oxygen level. It is used in soft drinks. It is used in dry ice, is also used in concerts and all. You will see that smog that is there on the stage, that is nothing but dry ice. Okay. Then CO2 carbon undergoes sp hybridization. Why sp hybridization? It looks like this. Okay, so two sigma bonds are there, so that is the reason it is undergoing sp hybridization, right? Then we can say two sp orbitals of carbons overlap to form p bonds. Two orbitals of this overlaps to form p bonds here as well. They form pi bonds here, right? P pi bonding with oxygen atom. Other two electrons of carbon are involved in p pi bonding. ठीक है, two orbitals are forming, two sigma bonds are formed, and two pi bonds are formed. You can write this here: two sigma bonds and two pi bonds. Okay, two sigma bonds and two pi bonds are formed, right? Then this results in linear shape with CO bonds of equal with no dipole moment, right? That's why they have a linear shape, and that's why their dipole moment will be cancelled. No dipole moment, the resonating structures are written here. This we have done in chemical bonding as well. Now let's see some of the compounds of silicon, right? Let's see silicon. Let's see silicon. Okay. If you see silicon, 95% of earth crust is made up of silica and silicates. Silicon dioxide, commonly known as silica, occurs in several crystalline forms. crystallographic form, quartz, cristobalite, uh, tridymite are some of the crystalline forms of silica. They are interconvertible at suitable. Silicon dioxide is covalent, three-dimensional. So what we are discussing here, that 95% silicon dioxide is commonly known as silica, right? Occurs in several forms. First is quartz. How many forms of SiO2, silicon dioxide? You have quartz, you have crystallobalite, you have tridymite. These are the forms of silica, and they are interconvertible, right? And it is also, silicon dioxide is also covalent in nature, right? If you talk about this three-dimensional network structure, it has SiO2, 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 okay, SiO2, 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 okay, that is how it is existing. So it is SiO2 is existing in like a three-dimensional structure. Each silicon atom is covalently bonded with tetrahedral to other four oxygen atoms, right? And what you will see, each oxygen atom in turn is covalently bonded to another silicon atom as shown. So each silicon atom is bonded to four oxygen, and each oxygen is bonded to one silicon. Each oxygen is one silicon, right? Each oxygen will have each oxygen will have two silicons. Wait a minute. Oxygen turns covalent to another silicon atoms as shown. Each corner is shared with another tetrahedron. That means each corner is being shared with other tetrahedron here. It's a giant molecule and they are forming eight membered rings. So can you see eight membered rings here? 1, 2, 3, 4, 5, 6, 7, 8. Eight membered rings. 1, 2, 3, 4, 5, 6, 7, 8. Eight membered rings are there. Eight membered rings are formed with alternate silicon and oxygen atom. Silicon, then oxygen, silicon, oxygen. Now with silicon, oxygen, silicon, this is how they are made. Okay. Then silica in its normal form is almost non-reactive. It resists the attack of halogens and all these, even at elevated. However, it is attacked by HF and NuH. With HF and NuH, it will be attacked. Quartz is extensively used in uh, piezoelectric material. It is made possible to develop extremely accurate clocks, modern radios, and television. So this is important, that quartz is used as a piezoelectric material, right? Then silica gel is used as drying agent and as a supporter of chromatography. If you remember, in chromatography also we have seen silica paste is used there, right? So it is also used in chromatographic materials, right? Mm, then there is this calciger and amorphous form of silica is used in filtration plants, right? Okay, let's see the next one, that is silicons. Now only the things that I am ticking, you only have to do that, okay? Silicons, they are group of organosilicon polymers. Now what is important, they have this kind of repeating unit, R2SiO. Starting material for the manufacture of silicons are alkyl or aryl substituted silicon chlorides. That is, this is the starting material, right? Starting material is this thing, right? We say starting material is this. This is the starting material. Methyl chloride reacts with silicon in presence of copper as a catalyst at high temperature. Various types of methyl substituted chlorosilanes of the formula MESICl3, MISICl2, all these are used. Hydrolysis of dimethylchlorosilane. Now here what we are saying, starting material is some alkyl chains will be there, some chlorine will be there, right? So overall it should be 4. Either 2 alkyl and 2 chlorine, or 3 alkyl or 1 chlorine, any of this you can use, or 1 alkyl or 3 chlorine, any of this you can use. Now let's say we are using 2 alkyl and 2 chlorine. Now when we are using this all reaction you don't have to do, just see what is formed in the end. You have SiR2ON. Isn't it the same thing? Isn't it the same thing? R2SiON. This is the unit. R2SiON. Just remember this unit that is being repeated. R2SiON. This is being the repeated unit here. Right? Just remember this unit, that's it. Right? That is called silicon. Silicon being surrounded by non-polar alkyl groups are water repelling in nature. So they are water repelling. Silicons are water repelling. They have general high thermal stability. They have high thermal stability, high dielectric strength, and resistant to oxidation and chemicals. They have wide application. They are used in sealant, greases, electrical insulator, waterproofing, etc. Biocompatible, they are also used in surgical and cosmetic plants. Okay, so these are the uses that you can do yourself as well. Then there is silicates, right? Till now we have done silica, that is SiO2. Then we have done silicons, that is R2SiO. This is the unit repeating. Little bit you must know from this thing, right? A large number of silicates mineral exist in nature. Some of them are, what are the silicates? They are like, you have feldspar, zeolites, mica, asbestos. The basic, what are these silicates? The basic structure unit of silicates are SiO2. Now this is important. They can ask you basic unit of silicates. Basic structural unit of silicate is SiO4, SiO4 4 negative, in which silicon atom is bonded to four other oxygen atom in the tetrahedral fashion. In silicates, either the discrete unit is present or number of such units are joined together via corners. Right? When silicates units are linked together, they form four chain ring or three dimension. Now, different structures can be there. Silicates unit are linked, they form chain, ring, sheet, ring sheet, or three dimensional structures. Different structures they can form. Negative charge on silicate structure is neutralized by a positive charge on metal ion. So they will have SiO4 4 negative, and that will be balanced by cation. Two important man-made silicates are glass and cement. Silicates, man-made silicates are glass and cement. These are man-made silicates. Okay, last is zeolites. That is a category of silicates. Aluminium atom replaced few silicon atoms in three-dimensional structure of silicon dioxide. When aluminium atom, they replace few silicon atoms in silicon dioxide, overall structure is known as aluminosilicate. Right? Cations such as these balance the negative charge. These examples are feldspar, zeolites. Right? These are the examples. Now, zeolites are widely used as catalyst in petrochemical industries and isomerism, that is Z. Now this is important. Which zeolite is used? ZSM5, a type of zeolite used to convert alcohol directly into gasoline. So this question is important. Which zeolite is used to convert alcohol to gasoline? That is ZSM5. Hydrated Hydrated zeolites are used in ion exchanger of hard water. So hydrated zeolites, that means these are used in hard water. Okay. So all the points that I have discussed here, okay, allotropes, so you know it's simple only, right? But what is silica? What is silicons? Like, what, you should have a rough idea about what is silicons. Then the uses, how they are used, all these things you should know. Okay. So now I'll be giving you break, right? ठीक है? Okay, so I'll be giving you break now, right? Yes. So I'll be giving you break and after I'll see you all at 7:30. Okay? At 7:30 I'll see you all. And this group number 13 and 14 we have completed already. And next is we are going to start with group number 15 today. Right? So today we'll be starting with group number 15. So I'll see you all at 7:30. Hello. So, wait a minute. So, guys, what I'll be doing now, ma'am. Ma'am, this topic is deleted. Arre, 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 arre. Don't be in that illusion that that topic is deleted. So, that is what I told you. Wait a second, I'll just show you that. What I have told you to do. Right? So, if you see this over here, actually, I'm not able to open the file. So, I don't know why I'm not able to do that. Actually, I'm not able to open the files. I don't know why I'm not able to do that. So I am not asking you to do all these reactions and all. Just do the uses. Okay? Because these compounds, all that is not in your syllabus. So you don't have to do these reactions and all. But you must know what is silica. You must know what is silicons, right? What is silicates? What is the unit of silicates? Only that much you should know, right? Otherwise, the trends and all before compounds, whatever I have discussed, is definitely in your syllabus and you have to do that, right? Okay. In your syllabus, you don't have compounds. In your syllabus, you have these things. You have this, what I call this exceptions, these trends that you have, atomic radius, ionization, enthalpy, all these trends that you have, this you cannot skip, right? This you cannot skip. And other things is you cannot skip some little bit, like what is boric acid. You should know that boric acid is BOH thrice. It's a weak acid. You should know it is not a protic acid. You should know, because that thing is related, it can be related to some other part of chemistry as well. So little bit you should know about that compound, not the reaction, nothing like that, just about little bit about that compound, right? Okay. So guys, today we'll be doing just this because my iPad is not working. I don't know why, right? I am trying to open the, yes, now it's opening, but the group 15 is not getting opened here. I don't know why. So I think now also, yes, as you can see this over here. So what I have told you here, not to do anything else, as you can see, I have already, you must know what is synthesis gas or what is water gas. It's a general thing about chemistry. You must know what is producer gas. Okay. So these are some of the basic things that you must know. You must know what is the structure of CO molecule, because it is used in chemical bonding. Then you must know greenhouse effect, though we all of us know. Structure of CO2 also we have done it in chemical bonding, that's why I have ticked it. You must know that H2CO3 is a weak dibasic acid, and in ionic equilibrium we have done that H2SO. This part we have done in ionic equilibrium. Okay, this is just to prove you that these things you cannot skip, right? Now this thing you don't need to need in detail, you just need to know what is silica, right? And where it is used, what is silicon, that's it, the formula of silicon. That's all what I have told you. Silicates, the formula is SiO4 negative, that's it. Then this much information you should know. What if they ask you, because you can't trust NT, right? Because they can ask you a little bit from outside as well. So this much only you must know. Okay. So little bit you should know. I am not asking you to cram all these compounds, right? Okay. So next class will be discussing group number 15 and rest of the part, right? Okay. So that's it, guys. Now I'll see you all in the next class. Till then, bye bye. Take care. Bye bye.